Magnetic flux. A magnet will produce a certain amount of magnetism, which is called the magnetic flux. Magnetic flux is given this symbol, which is the lowercase Greek letter phi. Magnetic flux is measured in units called Webers, given this symbol. Magnetic flux density, given the symbol capital B, which is measured in Tesla, capital T, is the magnetic flux per unit area. Or we can write that B is equal to phi over area A. So magnetic flux phi becomes magnetic flux density B multiplied by the area A. Therefore 1 Weber is the same as 1 Tesla meter squared. The crosses on the screen here represent a region of uniform magnetic flux density B going into the screen. You can think of the crosses as being the flights of arrows representing the field lines going directly away from you. Here we have a box of area A, which will enclose a magnetic flux phi equal to the magnetic flux density B times the area A. The magnetic flux density is represented by the density of the magnetic field lines. The magnetic flux is represented by the actual number of magnetic field lines. Here we have the end of a solenoid producing a magnetic field as shown, and here we have 3 rings, each of equal area A. Ring 1 has the most magnetic flux passing through it, with 5 field lines passing through it. Ring 3 has the least magnetic flux, only 3 field lines pass through it. Ring 1 has the greatest magnetic flux density, being magnetic flux divided by area. Ring 3 has the lowest magnetic flux density. Now we have 3 rings of increasing area. Each ring has the same magnetic flux passing through. All the field lines pass through all 3 rings. Ring 1 has the greatest magnetic flux density, being magnetic flux divided by area. So ring 1 has the smallest area, the largest magnetic flux density. Ring 3, having a much bigger area, has a lower magnetic flux density. Though of course generally on a diagram the field lines are drawn to simply represent the shape and approximate strength of the field at particular points, and you cannot do calculations based on field lines. Here's a simple example. A wire loop of area 15 square centimeters is perpendicular to a uniform magnetic field of density 75 millitesla. Calculate the magnetic flux passing through the loop. Well, for this we need magnetic flux phi is equal to BA, and putting in the values of 75 millitesla, 15 square centimeters is 15 times 10 to the minus 4 square meters, as there are 10,000 square centimeters in a square meter. This gives a magnetic flux of 1.1 times 10 to the minus 4 Webers. Let's just look at the case if the coil of area A is not perpendicular to the field. Like this, we have a magnetic field of magnetic flux density B Tesla, and now the coil of area A is at an angle theta to the perpendicular to the field as shown. So the component of the area that is perpendicular to the field, this line here, is given by A cos theta, and we found that the magnetic flux phi is now equal to BA cos theta.